Hi guys, Holloway here. Today's lecture is on moment of inertia. So there's 4 different concepts we'll be looking at today. So the first is moment of inertia for point masses. So when an object is a point mass, that means that the object has no dimensions. So typically they'll say something like it's a ball of clay, or it's a lump of mass at the end of a rod, or something like that. So I've drawn a little picture down here where we have our system consisting of 4 different point masses, and those are going to be arranged in such a way around a pivot that we need to figure out what is the distance from the pivot to figure out moment of inertia. So for this, remember, we're using the idea that I for point masses is mr squared. And so this comes from the always true statement that I is always equal to the integral of r squared dm. But for point masses, it simplifies to mr squared. So in your mind, you want to label each mass 1, 2, 3, 4 and go around kind of figuring out what is each one going to add up to. So mass 1 is going to be m1 times r1 squared plus m2 is, we don't know what that r2 is from this picture, but can you guys see that the r2 right there is not straight down? It's on a diagonal too, so you'd have to know some angles to be able to figure that out. And then you go on and do the same thing. You're going to add on m3 r3 squared plus m4 r4 squared, and that will equal I total for the system for those 4 point masses. If an object instead has dimensions, then we're going to use the I equals the integral of r squared dm. And we're also going to use the idea of density. So this is a rather tricky integration. So those of you guys not in calculus, I'm going to have you guys memorize the outcomes of some basic shapes that we see a lot. So again, I recommend everybody remember these formulas, but if you can learn to solve it yourself, it's a really good integration practice and very challenging. I have a couple of proofs, some other places you can look up. They're not in this lecture today, though. So the first one we're going to look at is a disk, and you can see here that there's an axis that goes through the center of the disk. So it rolls kind of like a wheel. So the important is how the axis is related to the disks really changes everything. So the radius of the wheel we measure from the axle to the edge of the disk, and then up here at the at the top, you see the height of the disk or thickness of the disk. That will not become part of the calculation. So this could be actually like a really long cylinder rolling, and it wouldn't change anything other than it's more massive. And so we account for the mass in there. But after you do the integration, we get I of a disk is 1/2 mr squared. So basically, anytime we have something that looks like a quarter rolling on the table, or pulleys, oftentimes they'll say they're a simple disc, or a long rod rolling on the table, that will yield 1/2 mr squared for the moment of inertia. For a hoop, so this is hollow in the middle, so there's nothing inside. It's like a ring or a piece of pipe, commonly called a hoop. When you do the integration, you get I is simply mr squared. So this actually should make sense because there's no mass near the axis. All the mass, every particle of mass, is all the way out here at the edge. And so all the mass is r away. So when we add it all up, they're all at that r. So it's mr squared for every particle. Next one, solid sphere. So I like to remember there's 2 types of spheres we have. So both equations have a 2 in them. When you do the integration, you end up with 2/5 mr squared if the sphere is solid. Now that's hard to remember, it's just a random fraction, but one little trick I remember is solid has 5 letters. So there's 2 types of spheres, and solid is 5 letters, so that helps me remember it's 2/5 mr squared. And this is one that there's a proof of online if you look it up in my notes section. The next one, a hollow sphere. So this is all the particles are on the outside, but you got to remember some of the particles are close, and so the circles as they go around get bigger the closer you get to the equator. So they don't all have the same radius, so it's not simply mr squared like it was for a hoop. This one ends up being 2/3 mr squared. So 2/3 mr squared is the moment of inertia for hollow sphere. And I can remember this is really goofy, I'm sorry, but a W looks like a 3 laying on its side. So I remember hollow ends with a 3 on its side, and that's how I remember it's 2/3. Again, there's two types of spheres. A solid sphere is 2/5 and a hollow sphere is 2/3. Next object is a rod. So this is a thin rod rotated about its center, kind of like spinning a baton, or like a propeller, if a propeller was made just of a rod. And so when you do the integration on this, you end up yielding 1/12 ml squared. Now you have to notice here, we're not using r anymore. We're using the full length of the rod. So we don't use an r here. It's ml squared, where l is the entire length of the rod. Now this one's only true if the radius of the rod is much smaller than the length of the rod. So if you had something that was kind of like this, and it was rotated about its center, so it had an axis going through it like that, and it was going around, that would no longer be true because this r now is relatively significant compared to the length of the rod. So we want the radius of the rod to be very, very small compared to the length of the rod. Once we get into here what's called a thick rod, it's a different calculation, and we should not get that. Thick rods are rather challenging, so they take a long time to solve, so that should not show up on the AP exam. Technically it's fair game, but it would be mean of them because it would take me about an hour to solve that to move on to the problem, just because I make so many mistakes. Not because it's that hard, but I make a lot of mistakes doing this. Now the pivot here is at the end of the rod, and so a rod rotated about its end is going to have a moment of inertia of 1/3 ml squared. So again, we're still using the full length of the rod, ml squared, and the coefficient is 1/3. So those are the 6 that are super common, so you should remember those. And then you should remember how you do point masses. So point masses are the sum of the mr squareds. The next concept we're going to look at, here's just as you're going through, you can look at this. I kind of put them in a table so it's a little easier to see. So you have disk, 1/2 mr squared, hoop, mr squared, solid sphere, 2/5 mr squared, hollow sphere, 2/3 mr squared, and a rod about its center, 1/12 ml squared, and a rod about its end, 1/3 ml squared. So oftentimes we won't have a single object rotating, but it'll be two objects that are kind of sandwiched together. So in this case, we have a disk welded to a rod. So really, it's two objects that are rotating. You've got to pay attention where the pivot point is. So in this one here, my pivot point is right here at the center. So it's a disk rotating about its center connected to a rod rotating about its end. So all we're going to do is we're going to add the two eyes for the two objects together to get the total eye of the system. So it's pretty common sense that you just take the eye of the disk and the eye of the rod and add them together, but realize that just because the disk is rotating around its center, the rod is not. So you have to look at each object compared to the axis. So a disk about its center is 1/2 mr squared. A rod about its end is 1/3 ml squared, and we simply add those together, plug in the right masses and radii, or length, like this is L of the rod. And this ends up not being able to simplify it, but if we had numbers, we could actually get a numeric answer for that. So again, if you have multiple pieces, we're just going to add them together and get the total. The last concept is one that most students don't care for. It's called I-parallel theorem. And so you read this as I-parallel is equal to the I through the center of mass of the object plus md squared. So this is when we have, if you take a look at the picture right down here, so for this picture right down here, we have a disk, and this disk right here is not rotating about center now. It's going to go through space around this pivot point right here. So the string or rod or whatever is so light we don't count that in this case. But the disk going around is not rotating around center, so it's not going to be 1/2 mr squared for the moment of inertia. So what we do is we go back and we're going to use the two parts of I-parallel. So we know I about the center of a disk is 1/2 mr squared. So that's going to go in right here. This first part for I of the disk is 1/2 mr squared, but to that we have to add md squared, and the d is the distance from the pivot from right here to where we know the I, which is about the center of the disk. So it's the total distance from there to there. So that'd be r plus L. And so that's what I put in. So I have the moment of inertia of the disk about its center, plus md, and the d was L plus R, and that yielded something that doesn't really simplify too much, but that would be the moment of inertia of a disk rotating in that kind of system. Okay, those are the 4 concepts for today. So again, you should remember that everything we're doing is based off I's integral of R squared dm. Although it's so challenging to do that in the amount of time given on the AP exam, we don't generally use that approach. So point masses are going to be mr squared. If it's a regular shape, you may be asked to try and do the integration. They oftentimes do that with a rod because rods are not that hard to do quickly. Otherwise, you're going to remember and put down one of the 6 that we're supposed to memorize. The AP exam does not say to memorize these, but it's really, really useful if you do. And then if an object has more than one shape, so it's made of a disk and a rod, then you can just simply add the 2 together to get the total I of the system. So we're just going to add them together. And then the final 4th topic we covered today is I parallel. So I parallel is only true when the known axis of rotation through the center of mass is parallel to a new axis some d away from the center of mass. So we're going to use I parallel when we have a new axis parallel to one we already know. And that's it for today. I hope that helps. See you next time.